analysis and measurement notes podcast. Go back to your notes outline and find Roman numeral 3 for chapter 2 data analysis notes. All right, you should see two different bullseyes here. And these illustrate the difference between accurate measurements and precise measurements. And if you look, this first bullseye right here, if you're trying to hit the bullseye, these are nice and close together. They're precise, but they are not accurate. Whereas accuracy, you're actually looking for close comparison to the standard. So if your bullseye is the standard, then you've got that made. In this case, maybe if you're trying to hit the, let's see, that's probably about the, is it 15 over there? I can't remember. I haven't played darts in a while. They're close together, so they're precise, but they're not accurate. These are accurate, but not terribly precise because they're not that close together. Okay, so if we're looking at measurements, we really care in chemistry about both precision and accuracy. Precision is how close the series of measurements are to one another, if they're reliable, if they're reproducible. That's usually reported as that deviation we saw in our measurement lab, plus or minus some part of the estimated unit when you're looking at the measurement scale. And you usually compare it to the mean for deviation as compared as an absolute deviation compared to the mean, or a standard deviation, which gets into a little more statistics. And if you're interested in going deeper into that, you'll have the opportunity to do that. Accuracy is measuring how close it is to the accepted value. Reported as percent error. Percent error is compared to, again, the true value. How far is your measurement away from the true value as a percentage of the true value? So if you have, if your test, the standard is 100%, and you got 90 out of 100, you've got an observed value of 90, the true value is 100, divided by 100 times 100, there's a lot of hundreds there. Then you would have 10 out of 100, which is 10% error, which is 90% correct, so that's pretty good work. We're going to skip this practice with measurement and be doing this in class, so keep that space open. Let's go through the rules for significant figures. A definition of a significant figure is one that has been measured, anything that's been measured. And when you take a measurement, as we already practiced, you include all the known values plus one estimated value. So if you were going to take a measurement of this, let's say it's a ruler up here, hopefully you would write something like 2.8 centimeters or whatever it's measuring. Could be 2.7, could be 2.9, but it's got to be some fraction of this space in between, somewhere in between here. So the times that the measurements aren't significant, or the numbers are not significant, is when they haven't been measured and they're there for some other purpose. For instance, zeros can be confusing. So in this case, if you measured 3 centimeters, but you wanted to record it in meters, you'd have to add these zeros to show the size of the number. In that case, those are just placeholders, and that measurement still only has one significant digit. If you have a number such as in number 3 down here, it's very small, but you measure 5030. Those are the numbers you actually measure, because these are all just placeholders. You get 4 significant digits. Here's a hint. Avoid the problem by putting this number in scientific notation. 5.030 times 10 to the negative fourth. That gets rid of all the insignificant zeros and shows you what was actually measured. So here you have a number like 600. Without context, you can't assume that those zeros are significant. You can assume it only has one significant figure. But if you use scientific notation, again, a really useful tool, you can communicate whether those zeros are measured or not. If you write 6.00 times 10 to the second, that's 3. 6.0 times 10 to the second is 2, and 6 times 10 to the second is 1. Excuse me. Anytime you have a number that's not a zero in a measurement, it's always significant. And zeros between two non-zero digits, also always significant. We'll practice more in class. Okay, sometimes the answer that you get out of a calculator is more digits than you can justify. So for instance, if you have a number 3.6247 and you want to show that it only has 3 significant figures, you'd round it to the first 3.62. Let's look at this number, 7.5647. For 4 sig figs, you would write 7.565. The 7 that you're rounding off is more than half, and so you need to round up to leave behind a 5. The next one, 6.2501 to 2 sig figs, 6.3, because you rounded off the 501, which is more than half again. Now here's where it gets a little tricky. If you have 3.250 and you only want 2 significant figures, what do you do with that 5? It's just straight in the middle. And in math, I know you usually round up. But if you always do that with data, you're going to end up with skewed data. So science has a rule. Okay, I have to get to the rule after I show the answers. For rounding, if it is less than a 5, you drop it, just like you would expect. If it's more than a 5, then you increase your value that you're rounding off to. But if it is 5 alone, no other digits after the 5, are followed by a non-zero digit, you round up. And if it's 5 just by itself, look at the figure to be rounded. If it ends in an even number, you drop the 5 and the figures that follow it. In this case, you're going to drop the 5 and the 0. In this case, 6.64, you're dropping the 5 here. Okay, let's look at this one again. 7.635. If you want to round it to 3 significant digits, you're rounding just to 5. You always want to round it so you end up with an even number. What that does, here it wasn't even, we left it even. Here it wasn't, we made it even. That means that with 5s that are rounded off, half the time they'll round off and half the time they'll round up, statistically on average. And that keeps the data from being skewed. Here we've got 8.105 rounded to 3 sig figs. We've already got an even number before the 5 that needs to be rounded off, so we keep it as an even number. Again, we're going to have to practice that. All right, couple rules for addition, subtraction, multiplication, and division, and what you do after the math. And then we'll be done. So when you add or subtract, your answer should be reported with the same number of decimal places as what you started with that has the fewest number of decimal places. Let's look at these numbers we're adding together. Not very likely that we're going to have to be doing this, but if we had to add these numbers, this one goes to the thousandths, This one goes to the tenths, and this one goes to the 10,000th. When you add them all up, the answer goes still to the 10,000th. We can't justify all of that because we don't know what are in these places that don't have digits. So you round it to the least precise location. Let me use another color here. If I don't hit the wrong button again. So the least precise location is the 10th. So I keep it so that I round this part off. It's more than half, so I round up. Okay, now to multiply and divide. Slightly different rule because it's multiplying a bunch of times, and it's an easy rule, but it doesn't make as much sense as the addition subtraction. So this is one you'll probably just want to memorize and practice using. When you multiply or divide, sorry about that, folks, you're rounding off to the same number of significant figures as is possessed by the term having the fewest significant figures. So let's look at these two numbers, 152.06 and 0.24. This one has 5 sig figs. See what you got for this one? 2, right? Good job. So your answer can have the fewest. The amount of sig figs is possessed by the fewest. Answer is 36.49. Round it off to 36 and you are done. All right, everybody, that's the end. Talk to you later.